Assalamu alaikum student. I hope you will be okay and fine. So today we will be discuss the valence bond theory in complexes. In the previous lecture you may remember that we talk about the basic valence bond theory, that how it is involved in the formation of simple inorganic molecule, but today we have to discuss it in coordination compound, that is complexes. So complex or coordination compound, as you may know very well, that it is basically a compound in which the transition metal accept the electron pair from the donor atom or a group of atom, which then make help to form a bond, and this type of bond is called coordinate covalent bond. So this is basically the sharing from the donor, and that donor is called ligand in coordination compound. So this is a little bit introduction of the complex, or similarly as see here that copper in ion form plus 2 state, and there are 4 ammonia ligand which come here and they give their electron pair to the copper ion, and by this they make a coordinate covalent bond, the 4 ammonia, the coordinate covalent bond, and this is the charge arises from the copper. So this is basically complex, or a complex sign present in the coordination sphere, and as you know, in the coordination sphere the central transition metal along with the ligand will be present, and the counter or the spectator ion remain outside. So this is basically the some of the introduction of the complex. Now we have to go through for the valence bond theory, that how valence bond theory make a complex, or how it will be useful in complexes. So as far as the other postulate are remains the same, which you may remember that in coordination in valence bond theory there are needed the empty orbital or half-filled orbital, and in coordination chemistry in valence bond theory there is no need of full shell orbital, or full shell orbital will be have no use. So in this case we can use the n-1 d orbital. As you know, in transition metal the d orbital is one less than the principal quantum number value, and ns orbital and p orbital or nd orbital take part in hybridization, and they first mix together and then they give us a new set of equivalent orbital having different energy from the previous one, and all have the same energy, and then they have unite with the help of a Vesper theory, and then they give us a certain geometry. So the hybridized orbital can overlap with the ligand orbital that can donate electron pair for bonding, and then the new structure of the complex can be formed. So we have to discuss this one by one in detail. So for this we have to reconsider the general electronic configuration of first transition series, or you have to know or recall the electronic configuration of first transition series, that is from scandium to zinc, and this is the ground state electronic configuration of transition element. So in this case you may know the number of electron present in d orbital. As you know, in transition metal the d orbital are is in the process of completion from 1 to 10, and there are some anomalies also in the transition element configuration which we may also study in the previous lectures. So going further we have to now look that how valence bond theory is helpful in the formation of simple complexes. So for this we have to see, or we have the first example of sp3 hybridization and the tetrahedral arrangement. For this we have to consider the bonding situation between a complex ion that has copper as a central metal and which has a ligand chloride ion around it, and the charge of it is -2. So we have to discuss this charge later, but first we have to consider the electronic configuration of copper and copper ion. For this you may remember the copper has atomic number 29, and it has electronic configuration of 3d 10 and 4s1. So for this we have to little bit remind you the exact electronic configuration of copper. So you may see that copper in the periodic table is located here, and then you may see the electronic configuration from the beginning: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d10. When you count all these electrons, so this comes to 29. But we are most interested here in the valence bond theory for valence electron. So our concern is for valence electron, as you know. So the valence electron ground configuration is 3d10 and 4s1. So all the other orbital are completely filled, and the filled orbital does not take part in hybridization or bond formation. So we have to go again and see that you may there see the normal copper configuration is 3d10 and 4s1 when but we have to look there here that here is copper plus 2. So copper plus 2 means that 2 electrons are lost from the copper. So due to this, the 4s0 and 3d9 configuration is formed. So going further, this is the energy diagram. This energy diagram you may see here also, that here is 3d10, but now after the formation of copper ion plus 2, we have this electron also lost, and one electron is lost from the 3d orbital. So this is the energy level diagram. The 4s orbital is lower than energy in the 3d orbital. You may here see the line, that these lines are joined here. So this means this is just to tell you that the what type of orbital are mixed together. So here you may see one 4s orbital and 3 4p orbital have to mix. So that give us sp3 4 sp3 orbital, and you may see all these orbital are empty. So again you may recall the name sp3. So sp3 means one s orbital is combined with 3p orbital, and you may see there is no participation of d orbital. So just there are the s orbital is added with 3p orbital, and we get sp3 hybrid orbital. So going further, now this is the unhybridized copper, in which copper plus 2, which has 4s orbital. 4s orbital has no electron, and similarly we have 3 4p orbital, and you have to look them from the color code, that this is the color code green from the top 4p, and this is the other loop of the 4p orbital. This is a blue 4p, and this is a blue, and this is, so this means there are three 4p orbital according to their coordinate system, that is 4p x, 4py and 4pz. But we have no concern right here about their coordinate system, because after the hybridization their coordinate system is also lost. So this is basically the picture of unhybridized copper in this state. But when it is formed mixed together, so then they form new orbital. So you may see how much orbital is added here. So here are 4 orbital basically added here, 1s and 3p orbital. So this means that we get 4 sp3 orbital, 1 2 3 4. So this is the shape of hybridized copper orbital. So 4 copper orbital are overlap with each other, and when these orbital are overlap with each other, it make a tetrahedral structure. This tetrahedral structure is, you may recall, the same that we said in the Vesper theory, the electron domain. So basically these are the electron domain, or mean that there are some of the domains of the orbitals. So orbital domains, so four orbital domains can add with each other. So you may see here that in the previous slide these sp3 all four orbital are empty, but now here is a little bit different scenario, that here you see electron pair in each of the sp orbital with color blue color coding, a new color coding. So this is just like that there are four pair of electron from the four chloride ligand comes here. So you may remember that we are making the complex with the help of a ligand. So ligand, there are four chloride ion. So chloride ion has extra electron, and each electron can add here, and this addition of electron can give us, so these electrons are present in the 3p orbital of the chloride ion, and each 3p orbital can donate electron pair. You may see here electron pair from this side, and from all possible four sides. So basically, according to valence bond theory, it is a linear or head-on collision. So this is basically they are forming four sigma bond. So you may see here that this is sp3, this is sp3, this is sp3, this is sp3, and this sp3 is make a bond from 4 chlorine, and the bond, the orbital from chloride ion is basically 3p orbital with electron pair. So remember, this is a chloride ion, not a normal chlorine or a neutral chlorine. Chloride ion with minus extra minus charge or pair. So this means after making or addition with the copper, so copper has plus 2 and chlorine has 4 minus, so these 4 minus can then add with copper and forming the total coordination sphere charge give rise to minus 2, so which you may understand that how the charge of the coordination sphere makes comes minus 2, so you may understand now. So this is the first example. Now we have to move and in this example you may see that according to valence bond theory, just s and p orbital take part in hybridization, but there is no participation of d orbital in hybridization. But now we have to going from for another case. In this case we may see that d orbital is also take part in bond formation. So this is, in this example we have to see that d orbital also take part in hybridization and the formation of a complex. So for this we have to consider the complex is contain nickel transition metal as a central metal ion. So for this, the electronic configuration of nickel you may see here, but you may see a separate electronic configuration here also. So this is the position of nickel. The nickel position is just quite neighbor to the copper. So copper has 29, which we just recently studied, and before copper it is nickel, so the electronic configuration of nickel is 28. And as comparing the electronic configuration, so this is the similar electronic configuration with a slight difference, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. So just considering the electronic configuration of the nickel with the copper, you may remember copper has 3d10 ground state electronic configuration with 4s1, but here there are two electron in 4s orbital and one electron in the 3D orbital of the fourth and fifth orientations. So this is implies due to the Hund's rule that at ground state the two electron, if the space is available, they occupy singly or they goes in a single orbital or without pairing. So you may remember that this is basically a Hund's rule. So according to Hund's rule, they occupy a separate or single position. So this is the electronic configuration of nickel. We have to compare the valence shell electronic configuration of nickel. Again, nickel has 28. The valence electronic configuration is 3d8 4s2. This is the ground state electronic configuration when 2 electron is lost. So the 2 electron, basically the 4s2 electron, basically they are lost. So these are called the valence electrons. So basically these are lost and then making the 4s 0 orbital. So as far as the concern, so nickel has this type of situation, for example, which contain the upper orbital, that is 4s. So 4s orbital is their inner, and this is the upper orbital of the 4p orbital, which has no electron. So according to our principle, if you remember that if we go upward slightly, so this may arise 4p orbital and then 4p, then 5s and then 4d orbital, but we have to consider just these neighboring orbital which are there. So these are the 4p orbital. You may see and understand with the color coding. That is, the one orientation of 4p orbital is with green, the other orientation is with blue, and the third one is with red orientation. So as I told you before, that we have to ignore here 4px, 4py and 4pz. These are three orientation, but we have two, and these are the coordinate line. But after the hybridization, these coordinate lines are lost. So then there will be no coordinate line, and then new hybrid orbital can be made. So going further, we have to check before that you may remember here in this case that there in this d orbital the single orbital is present in fourth one orientation, and the single electron is present in the fifth one orientation. So when in the ionized state, when nickel is rearranging themselves for bond formation, then the Hund's rule concept is little bit violated, and this electron is migrated here and leaving this orbital vacant. So you may remember that this electron has to be transferred here, and after this the fifth orbital will be vacant. You may see this in the next slide. Yes, this. So here you may see that these are the 8 electron. Before these are also 8, but one electron is present here and one electron is here, but this electron is shifted to here and leaving this 3 d orbital vacant. So by seeing the line, you may see here the line. So this line means that these orbital are combined with each other and they are mixed to give you the hybrid orbital. So you may remember each hybrid orbital has the name according to their combination orbital. So you may count here. So here is d orbital is 8, s orbital is 8, and total 2p orbital is 8. So therefore their names has to be dsp2. So this means that each orbital contain the d contribution also, the s contribution also, and p2 configuration also. This means this contain 2p orbital. So the four dsp2 orbital are formed. And remember, you may notice here that the third one, 4p orbital, does not take part in bond formation. So that is due to all the orbital take part in bond formation which are in the dotted line. So this last one, 4p orbital, does not take part in bond formation. So the total number of the orbital here are 4. So then they make 4 vacant dsp2 orbital, and you have to there see that these are the 3d orbital which are going here. So these are first, the 3d orbital have 5 orientation, and now the 3d orbital has 4 orientation. The fifth one is goes toward hybridization, so it take part in hybridization. So after this, you may see this electron has in the same energy, and you may see in the energy level diagram that this orbital is little going upward, this and this orbital little going downward, and then the 4 dsp2 orbital all have similar energy, but this energy is totally different from the previous one. For example, some orbital joining to making the dsp2 orbital are in very low energy, some are in very high energy, and so this is the intermediate one. And after this, so this dsp2 hybridization and square planar arrangement can make. So let's me before explain you the square planar arrangement. First, you may see that these are the 4D sp2 hybrid orbital 1, 2, 3, and 4, and this is basically the nickel, which so nickel now goes toward the hybridized state. So you may see in the Vesper theory that there are two possibilities to making the 4 orbitals. So some orbital goes toward tetrahedral and some orbital goes toward the uh, square planar geometry. So some people have a confusion that why it's happened that not all the orbital going toward tetrahedral. This is because this is the participation of 3d orbital. Basically 3d orbital has a dumbbell shape and it has a little bit very awkward shape, so it is not readily available that these make the dsp2 hybridization goes toward tetrahedral structure, so they normally goes toward the square planar structure. So now going further, so this dsp2 hybridization can give a square planar arrangement, and you may see here that in the nickel the ligand here are the basically the cyanide. So basically cyanide ion has also a negative charge and it has electron pair. So cyanide ion make their electron pair here in these vacant 4d sphere orbital. So there are total 4 cyanide ion, and each cyanide ion has a pair of electron. So every cyanide ion has put his electron pair in 4 vacant square planar dsp2 hybrid orbital, and these electron are the previous electron, and so basically this make the structure of nickel tetracyanide. So let's see 3D geometrical shape. So this is basically a 3D geometrical shape of nickel cyanide. In here you may see that there is a nickel which is lies on the plane and square planar form, and these are from the each side. These are the 4 cyanide molecule which overlap its bond with the uh, dsp2, and similarly carbon has also has sp hybridization, and this cyanide and has electron pair. So each cyanidine gives electron pair to dsp2 hybrid orbital. So this cyanidine add from here, this cyanidine add from here, this cyanidine add from here, and you may see cyanide has carbon and nitrogen in its structure. So basically this is the 3D shape of the nickel tetracyanide -2 complex sign, and it has the central square planar in shape. We have also some of the another quick example of the which contain also a d orbital. So let's we have to study the another example of hybridization. In this hybridization, there is 2D orbital taking place in bond formation. So there are, so that is why its name put D2sp3 hybridization, means there are two D orientation, one S, and two total 3p orientation. For this you have to remember or the studies the electronic configuration of cobalt. This is normal cobalt. So basically cobalt has electronic configuration. You may see there are around about 7 electron in 3d orbital and 2 electron in 4s orbital. So this is basically a ground state electronic configuration. For plus 2 means that we have to remove these 4s2 orbital, so making the similar electronic configuration but without 4. If we make cobalt plus 3, so plus 3 means that along with 4s2 orbital removal, we have also removed one electron. So by removing one electron, this electron is also make single. So this is and this is the other neighboring orbital. You may see the 4p orbital in each of the case of copper and nickel also. So if you remember that after the removal of electron, what take that these two electron are make a shift. So this electron goes here and this electron goes here. So by emptying these two 3d orbitals, so if you count the electron, 1 2 3 4 5 6, so there are total 6 electron. So we have to make a pair, or then the electron look like this. So now in each 3 orientation of 3d orbital there are pair of electron, and we and the cobalt plus 3 ion make a transition, and this transition means that it make available their 3d orbital for hybridization also. And so now they are empty, and we have 1 2 basically 2 d orbital, and this is lower one the similar 4s orbital, and from uppercase now we are taking all the 4p orbital. So by making we are totaling combining 6 orbitals. So there are 3 orbital here and 3 orbital here. uh, so these are basically due to this, these are D2sp2 orbital. The figure is a little bit blur, but you have to be compromise with it, that how the three lower orbital is adding with the higher 3 orbital of 4p, so giving us basically 6 D2sp2 hybrid orbital, and this is the similar electron. So after adding this situation, now the cobalt has 6 orbital. So you may see here the similar cobalt atom with the non-hybridized state, but when these hybridized 6 orbital came here, so these 6 orbital are here. And according to, similarly, if you remember or recall in the Vesper theory, if you have 6 electron domain, you get octahedral shape. So basically cobalt rearranges itself central atom, it's from the octahedral shape. So these are basically the 6 orbital. 4 orbital are attached themselves as a square planar position, one from the top and one from the bottom. So after it, now we have to come 6 ammonia molecule, and this ammonia molecule can add here. So this ammonia molecule can put their electron pair in the 6 dsp2 molecule. So there are, from the color coding, you may see the new 12 electron come from the 6 ammonia molecule, and each ammonia molecule contribute 2 electron. So this ammonia molecule contribute 2 electron and making the orbital fill. So now let's see the new shape. So the new shape is little bit complicated, but you have to see in the center, basically in the center there is a cobalt 3, the similar ion hybridized state which you see here. So basically you have to memorize this picture or this shape first, and then you have to put this shape in the center. So basically this is the cobalt 3 in the center. So now from the sidewise, for example, if you see from the upper side, this is basically nitrogen, this is the 3 hydrogen, and this is the lone pair of electron which ammonia contain, nitrogen contain. So these 2 electron from the ammonia attach linearly, or for example they attach themselves as head-on collision, or they making in the sense of sigma bond in each side of the D2sp2. You may see here D2sp2 hybridization, and here is also D2 hybridization. So you may see here the 6 ammonia molecule, 1 2 3 4 5 and 6. So basically there are 6 ammonia molecules surrounding the cobalt atom. So this is a little bit a clear picture. If you have to be, I have to put here, so you may try here. Yes, there are the cobalt atomic number 27. This is the ground state electronic configuration, and by making the cobalt 3 ion, so the loss of 3 electrons, so these 2 electrons are lost, and similarly 1 electron is lost from here, so making available 3 electron. So basically there is a addition of 4d and 2 4d, 3 4p, and 1 4s. So basically you have to reconsider yourself again to the line. So if you count all the orbital, there are 6 orbital, and similarly by changing the fluoride ion also take part in bond formation. So basically you may see that if instead of ammonia ligand, if you have fluoride or chloride ligand, so the 6 fluoride ion may come here and they make a bond with cobalt, and this bond is basically a coordinate covalent bond. So basically this is electron pair from one fluoride ion, this electron pair from the other fluoride ion, this electron pair from the other fluoride ion, and this electron from the other, and all the 6 can make a bond. So you may now understand basically the formation of some of the basic complex compound with the help of valence bond theory, and there are some of the simple example, or you have to be studied and you have to be see, and you have to be get a practice on the valence bond theory. So uh, you have to see, and we have to discuss this example in class also. So thank you.